Welcome to Hitex and to today's webinar, How do I test efficiently across all test levels, with Thomas Schütz from PROTOS. My name is Wolfgang Fuller and I will give you a short introduction about Hitex before the webinar starts. Hitex was established in 1976 as an embedded development company and has achieved rapid growth by developing and providing microcontroller development tools. With a global network, a branch in the UK, and many strategic partnerships, we ensure a presence wherever it is needed. Today, Hitex as a proven expert is also in great demand as a service provider for training, consulting, test services, development, and production services. Hitex supports all phases of your project from the idea to the finished system. With over 70 employees, most of whom are developers and engineers, Hitex has excellent expertise and enjoys an outstanding reputation. Hitex is the preferred design house for all major microcontroller families from Infineon and an important distribution partner for ARM HIL tools and tools for hardware and software testing also. In today's webinar, you will learn about what should be tested at which level and how to find the optimal method for each testing challenge. During the webinar, you will have the opportunity to ask your questions via the webinar panel. The Hitex team and Thomas Schütz will answer your questions by email afterwards. Our presenter today, Thomas Schütz from PROTOS in Munich, is about to give you a brief introduction to PROTOS and of course of himself before we go into the webinar.
The topic today is how do I test efficiently across all test levels for embedded systems. That's always the context where we are. And which test methods and simulations do I need? So just a word about PROTOS. Who is PROTOS? We are a software company in Munich, and we focus on developing software tools, test tools, and software architectures for embedded systems. And today we're talking about the test tools. So I am Thomas Schütz. I'm an aerospace engineer with a fable for embedded software architectures, tests, and tools. And so why are we doing what we're doing? And why do we want to test on different test levels? Let's have a look at the costs related to retesting. So the cost to fix a bug and to retest are growing usually exponentially with the phase of the project. So of course, if you detect a bug during implementation, you fix it, you retest it maybe as a unit test, that's relatively simple, fast, inexpensive, and so on. Later in the process, in integration test phase or system test, system integration phase or system test phase, it gets really expensive, and it's also very late in the process. So you might need to wait a month or so for the next system test because it's prohibitively expensive to test more often. And of course, after release, that's a big catastrophe. So what we try to do is always, so what everybody should try to do is to bring the test levels as close as possible to the implementation with a good cost-benefit relation, of course. So if we bring, for example, the system test, if we can run a system test automatically at the beginning of the development process already, so you change something in your code and you can automatically run a system test, that's relatively inexpensive and very fast. You can fix the bug and so on. We need to learn and test earlier. That's the big message here. Now let's have a look at where tests usually happen in the development process. So let's assume we start with an evaluation board. We commission some drivers, some hardware-related software components. Then on top of that, we have our software components that usually define the logic of the application. And we integrate everything together into an application. And eventually we move to the real electronics, to the real ECU, electronic control unit. And then at a certain point, we want to deliver. So now where are we testing? So the unit tests can be used to test pure software components. if they are synchronous, and that's a really good test, relatively inexpensive, very good to automate, so please do that. But you cannot test everything here on that level. Later in the process, you might want to use a big HIL system test, hardware-in-the-loop system test, to test your complete application on top of your real ECU. And later in the process, you might want to run a real system test. So you get into the car and you drive around the block. That would be a real system test. With a HIL system test, you would simulate the car, for example. Now, as we can see, there's a relatively big area where we cannot really test. So, and that's where the hardware-software integration test with our mini-HIL, for example, comes into play. The goal here is to make an integration test on the chip, on the real microcontroller with your complete software stack. So you're testing already the real software as it is delivered on the real microcontroller, for example, on an evaluation board, but you leave away all the expensive and dangerous stuff in the HIL system test or the system test, but you already can test the complete logic. Unlike the unit tests, in the unit test, you only can test parts of your software. So that's the idea here of those different test levels. Now let's have a look at the focus of the test levels and the methods. Now let's talk again about the integration here. We have we start with the software units. We build them together to the application software. Then we integrate the drivers and the software on a microcontroller. Then we use the microcontroller on an electronic control unit together with maybe some power electronics, some sensors, some actuators, and so on. And in the end, we have a system. In this case, maybe a hydraulic system for a car or a lubrication pump, something like that. Could also be anything else, like a medical system or whatever it is. So with a motor, a pump, and a hydraulic system. So let's go with this example for our webinar. So on the lowest level, usually we can use unit tests for single C modules or classes in C++, Java, whatever it is. And we use a unit test tool to do that. So in the strictest sense, a unit test is really just for one unit, so for one C module. One level up, we talk about software integration tests. You still can do this with unit test tools. So you bring together several units and test them together. So you can test relatively big part of your software on that level. And it's inexpensive to implement if you don't overdo it. So don't overdo it. And it's really good to automate. But there are still some units you cannot test really good with a unit test. For example, if you have something asynchronous like a motor controller, state-based behavior, or some communication protocols or whatever it is, that's hard to test with a unit test. So if it's asynchronous and so on, that's hard to test. So, and you also cannot test the drivers because, yeah, the drivers, you have attached hardware, signals, pins of the microcontroller, so that's really hard to do. Another benefit of the unit test is you can usually run the unit tests on any computer, so directly on the continuous integration servers. You do not need real hardware, real microcontrollers for that. So the next level would be a hardware-software integration test. Some call this the processor-in-the-loop test. We call it the smallest possible hardware-in-the-loop test. You look at the microcontroller as a black box and you test at the pins of the microcontroller. You already can test the complete software as it is delivered, including drivers and the complete application software. Now, next level up, the big hardware-in-the-loop test that already includes the complete electronic control unit, for example, with the power electronics, with sensors, with actuators. That's already much more expensive. It gives you a bigger scope, but you cannot test so many details. So the further you move away from your software, the less deep you can test your software, of course. Yeah, but the advantage is you can test more of the hardware. The next level would be the system test, where you actually really build the system together and test it in real life, whatever that means. So there are a couple of other tests I want to mention. So static code analysis is something you can run really good on the unit and software integration test level. You can also use, instead of doing this automatically, you can use reviews. Reviews are always a good idea to improve the quality, especially not only of the code execution, but also of the design, for example. That's very important. Then there are other tests on the higher levels. They can also be done manually. Yeah, for example, you take your lubrication pump, you push a button, and you see whether the oil comes out for a minute or not. This would be a manual test, and it's interesting. A lot of projects really heavily rely on manual tests, and on system level, this might be a good idea if you do not have, let's say, so expensive products that allow you to build an automatic system test, for example. Then probably manual tests are not such a bad idea, but we should aim, at least in the lower level test levels, for automation. So now the gradient here from unit test to system test is unit test, and you can run this it's fast, you can run this very often, it's inexpensive, and it's really easy to automate with continuous integration. And the further you go down, the more expensive it gets, the slower it gets, and the harder it is to automate. So a system test is usually really, really hard to automate. So up to, let's say, the smallest possible hardware in the loop test, things are really good to automate. And yeah, hardware in the loop test, a big hardware in the loop test is already really expensive to automate. And the equipment is really expensive, so it's never there for automation. So because it's used in several projects. Now, all test levels need a test harness. So let's talk about a test harness a little bit. A test harness for a system or a component under test always has test cases, and it also needs some kind of environment simulation. Because, for example, if you have a piece of C code, you need not only the test cases to call the C code, but you need also to satisfy for the system under test, in this case, a C function, for example, it might call other functions in your system, and you need to stop or mock them, because if they're not there, you cannot even compile your test, or you do not get relevant results for your test cases. So this both ends together are called a test harness. Now let's have a look at the test harness for unit tests. For unit tests, you have a synchronous test execution. So you call a function, you're blocked until the function returns, and you evaluate what happened. Yeah, and what happened maybe in the return value, but you could also evaluate the stubs and mocks you call to simulate the environment. So that's the other end. You need to satisfy at least the function calls for compilation with a stub or with a mock that gives you back a little bit more information than a stub is usually just to be able to compile something that gives back one value, fixed value. A mock would already be a very, very simple simulation of some kind of behavior. So, and that's all synchronous. For an integration or a system test, you need asynchronous test cases, because while you're sending a command, for example, the motor is running while the bus system is running and the temperature is controlled and whatever it is. So it's completely asynchronous. So you need asynchronous test cases and also asynchronous environment simulations. Usually you use closed loop or open loop simulations. Closed loop, for example, if you want to test a motor control with a closed loop motor controller, then you need a closed loop simulation to simulate the motor. For example, for something like a temperature simulation, usually you get away with an environment simulation, with an open loop simulation. You just set a fixed value and that's it. Depending on the system you want to test. So usually in the core, you need a closed loop simulation, surrounding things like error sensors or something like that. You usually get away with open loop simulations. Now, the message here is you need more than test cases. So you might need 5 test cases, but 5,000 mocks. That's really expensive, even if you only want to run 5 test cases. So think about that. Now, let's start with the unit test. What can you do with a unit test? The main goal is to test the correct implementation of software functions and software modules. So you really want to test whether the implementation of this unit is correct. So it's usually a test against a specification. In some cases against the requirement, but very seldom against the user requirement, because it's so much down inside your software that usually a single unit usually never is attached directly to a user requirement, for example. The pro for unit tests, also for software integration test, is they're easy to implement, they're easy to automate, they're early in the process, and they can give you very high code coverage, for example, 100% for MCDC or something like that. So this might be needed for safety critical systems, but many complex errors cannot be detected at this level. They happen on integration or on system level. So for example, a jitter in a PWM or something like that, that might lead to a problem in your software. That's something, that's really hard to detect if you do not have a PWM attached, real hardware attached to the system and so on. Or also, you cannot test for asynchronous and concurrent elements like a motor controller, battery controller. You can do this on unit test level, but it's just not made for this kind of behavior because it's a synchronous test. So you need to build something on your own. So it's better to use other methods for that. You also cannot test drivers because you need to attach some hardware, and this also might be asynchronous and so on. And it's a lot of work if you overdo it. So if you start with 100% unit test code coverage, you might use a lot of effort or put a lot of effort into something that doesn't really detect the complex errors. So that's probably not, it's a good place to start, but don't overdo it. In the end, you can clean up with filling the gaps with unit test. Now, next level would be the hardware-software integration test. So the hardware-software integration test, processor-in-the-loop test would regard the microcontroller and maybe plus some other chips as a black box. You always test on signal level, usually. So no power level, but only signal level. And the main goal is here not to test a single component, like, for example, the motor control or the error control or something like that. You can do this maybe for pure software components better on a unit test level, but you want to test the integration of the component with the software system, including drivers and electric signals. The pro is you can put your system into almost any state to test it by changing the simulation for failure injection. So for example, the ADC for temperature, you can manipulate this just by attaching a signal from analog value from a DAC, and by that stimulating any kind of temperature you want. So it's really easy to do failure injection. So many error paths can be tested without actual hardware. So if you have real hardware attached to a real motor, this can be really hard to do because you need to destroy the motor to really get the error situation. You can also do this really early in the process. It's easy to automate if done right. and you can test the complete unmodified software, including all the drivers. This is very good to find a lot of errors, and it's also very good to for certified products, for example, safety critical products in automotive, in avionics, in medical devices, and so on. Some of those standards there require to test the unmodified software, and with a unit test you never have unmodified software. So that's for some application, that's the first level where actually can run safety critical tests here. The con is you cannot test the electronic system completely, so the ECU. In many cases, you also need a system test. So usually it's not entirely sufficient to test on that level, depending on the application you have. There are applications where it's almost a system test on this level. If you only have a little bit of electronics attached, if you have a huge mechanical or electronic system attached, then you might need another system test there. The medium code coverage is between 70 and 90%, which is relatively high for a couple of tests already. But for example, things like MCDC you cannot test on an integration level. So the higher you get on the level, the less coverage you get. But you can, it's astounding, you can get on that level maybe 70–80% code coverage with just a couple of test cases. That's really efficient, done right. So example would be, for example, if you want to test the temperature shutdown or error shutdown for a temperature sensor, for example, you inject a wrong temperature just with a analog value on signal level, so 3.3 volt or 5 volt or something like that. Then the black box behavior, so it's a black box test, cascades through your software application. And then you want to measure two things. For example, whether the PWM is off after 100 microseconds. So why do you want to know this? Because if I have a safety critical temperature error, I want to make sure that the motor stops. That would be a requirement for a lubrication pump or for a motor control system or whatever it is. And at the other end, on the application end, on the user end, I want a correct CAN error message for this situation, because if a crane is attached or a oil rig or something safety critical is attached to this system, then you need to inform the other system that that the system is broken, that the component is broken, and this would be an example for a safety critical failure injection test. You can do this with all the sensors because it's only simulated. Now let's go to the big hardware in the loop system test. The main goal is to test the complete ECU or the complete system. The pro is you can test the complete ECU, including software, microcontroller, and the electronics hardware. In many cases, this can replace the real system test, depending on the situation, of course. And the cons are there's much more effort and costs involved for testing and failure injection. So for example, for making failure injection for a temperature sensor, you need a climate chamber. That climate chamber is much harder to do and much slower, much more expensive than just to change a 3.3 volt at a sensor. Then many error paths cannot be tested because you would need to modify or destroy the hardware, like a motor. You would need to destroy the motor or manipulate the motor to simulate a real motor problem for failure injection. And the hardware in the loop, the big hardware in the loop system, is usually available very late in the development process, so you do not get early feedback. Typical injection would be temperature too high in a climate chamber. This takes ages in a climate chamber. For example, 2 hours to change the temperature from plus 50 degrees to minus 40 or something like that. this can be done on the lower level in a millisecond or so. So then the next point is the microcontroller software here reacts, and at the power electronics, the motor power is off. So for example, you would really measure whether the power is off. Also, again, it's much harder to do, much more expensive, but you really know that the ECU works. So there are always pros and cons. And last but not least, that would be more or less the same like on the lower level tests. Whether the correct error message comes out of the system. Now let's have a look at the stubbing, mogging, and simulation. Stubbing and mogging for unit tests. So stubbing is just replacing the real function or component with a simplified version and return a fixed value. To satisfy the compiler, you need to compile, of course, your test cases. You can run out so the test without a real dependency to your project. Mocking would already be a little bit more like you create a fake object or a function that also replaces the real dependency, but also, for example, tracks what happens, has a very simple behavior, returning different values, maybe interacting with other mocking objects. So it's already maybe a little simulation. The general problems are if the software architecture is not modular, mocking and stubbing and unit tests can be a really expensive challenge. So you need to have a good software architecture to really make a good unit testing. It can become really, really prohibitively expensive if you do not have a good software architecture to test on that level. Yeah? So even with a good architecture, unit tests can be a lot of effort for a very high code coverage. So keep that in mind. Now, simple unit tests with a stub object as an example. You have here your system under test. So that's wrong here, under test. I'm fixing the slide live. So that's, I love to do that. So already fixed. Now you have the system under test, for example, a filter. So you call a filter and it returns something from a value, from a sensor value. And the test case would, for example, be expect equal, get processed value, 20, so it calls the filter, and the mock object would be the read sensor value. It returns in this case 42, and we also could add get processed value for the test case. So that's the value we actually get from the test case. So we call the filter and then we get the sensor value and verify them whether it's okay or not. The example would be with Google Test Framework here. Now, if we go 1 or 2 levels higher, integration and system tests, they're asynchronous, so usually they need a little bit different mocking and stubbing, so they need simulations. There are usually 2 different kinds of behaviors we want to simulate. One is a state-based and event-based behavior. We can do this really good with state machines, so environment simulation for state and event-based systems or part of a system. And the implementation, for example, for interface protocols that are needed for tests, so CAN protocol or whatever specific protocol, UART protocol, or whatever you have, that's really good to implement with state machines. So next modeling would be data flow modeling, for example, with something like Simulink. It's very good to simulate open or closed loop system, especially closed loop systems. For example, the motor, you want to control over motor control. If you do not want to attach a real motor, you need an environment simulation for the real motor. And this can be done really good with data flow modeling, Simulink, Scilab, or we also have something integrated for our test tooling, data flow modeling based on Room. So that's a really good way to simulate environments. And they're all asynchronous. So they have states, they have behavior, they have values, they have continuous behavior. Now, we also can use models for the test case definition, not only for the environment simulations. For example, a classification tree. You might know the tool Tessie, which is also sold by Hitex, and they provide you with training and services around Tessie. And they have a classification tree in Tessie, which is really nice to have a structured analysis and generation of test cases. Really nice tooling there. Then another tooling or method would be state transition testing. It's not about testing state transition diagrams. It's actually a redundant black box description of the expected system behavior. So you define what you expect of your system. Doesn't matter on which level. Could be a unit test level, could be a system level, could be an integration test level. Also capable of asynchronous testing. And you can really fast derive with a code generator needed test cases to cover the happy and unhappy paths. A very efficient way to generate a lot of relevant test cases. It's very good for robustness tests, for safety critical tests, and so on. And last but not least, you can also use sequence diagram to generate test cases or to visualize test cases. That's a really efficient way to understand what your test case actually does. It's very good for description and documentation of test cases. It provides a graphical view on the test cases and the test execution. And it's easy to understand also for non-developers and non-testers. So you can discuss with them, now I push this button, what happens in my system, the LED goes red or whatever. You can really understand this also as a not software developer or not test developer. So sit down together with your system developers and use models to discuss what your system actually should behave. Now, I'm focusing now a little bit more on the integration test level, system test level. We have a so-called mini-HIL hardware to support this kind of test levels. So, for example, at Kercher, they're using this for all their products. That's the processor in the test loop. So it's the system under test is the processor with the complete software and the complete drivers. We connect this with the other side here, with our test system. So that's the evaluation board, and we connect all those digital, analog, SPI, and so on signals with our test system. You can also connect this over a 24-volt adapter to run system tests. It's also possible, but let's focus on the middle ground here. And now on this side, you need three things. You need the connection of the signals into your test software. It's the first level. Second level is you need to simulate the environment. For example, if there is a motor, you need to simulate the motor, the temperature sensor. You need to simulate maybe the battery, and so on, because this you want this processor to run unchanged from software perspective, unchanged in the simulated environment. And then you can start to put test cases on top of that. So signals, environment simulation, and test cases. Now, how do we do that? We have a model-based development environment to define structure and behavior for the environment simulations and the test models, and also the signals. Then we generate the code. Here you see, for example, instead of the STM32 board, we have an Oryx board here, Hitex Oryx board, and an adapter to adapt the signals to the mini-HIL board here. And then we generate, compile, and flash the code. It's C code, generated C code. We flash this to the microcontroller because this needs to be hard real time. Because if I want to simulate, for example, a motor system, this needs to be simulated with 20-30 kilohertz for a BLDC motor. So I cannot do this on a personal computer and attach this to a hard real-time system. And then the test cases run, the simulations run, and we get those diagrams as results. So we convert the results into meaningful diagrams for us as human beings to understand what happens on the various levels of tests. So more the manager view or more the developer and the test developer view. And then we learn and iterate. A cycle takes maybe 1 minute, couple of minutes to run a complete test. Now I'm going to run a little demo just to give you an idea what it looks like. I have just a second here. I have here the system, the test system as a model. As I said before, we're modeling everything as a model. It's a room model, real-time object-oriented modeling. Here on the lowest level, we define we have the adapters, the model adapters for the IOs. For example, a duty capture unit for the 3 PWMs of a motor simulation, for a motor simulation that simulates a BLDC motor with 3 PWMs block commutation. And it generates Hall signals to simulate what the real motor would do. And we feed this back into the system. So just to give you an idea what this looks like. So that's the system under test with the motor simulation, and that's the simulated motor, not with the motor controller, and that's the simulated motor with the test cases. So we're talking about this part here. And this box here is basically generated into the test system. So here we have analog, digital adapters. Then on that level, we have the simulation. It's just a small example, but that's what a real test system looks like. And yeah, here we simulate the motor as an open loop simulation, the motor, the temperature, I mean. The motor is simulated as a closed loop simulation. In this case, I'm using a state machine. Could also be a data flow model, either from Simulink, generated C code from Simulink, or also in our own method, data flow model. Then last but not least, we need a test case. Again, a test case needs a behavior. And this behavior is, again, a modeling language. It's a textual modeling language. By the way, all our languages are textual languages. So even those graphical views are internally textual models. So you can diff them, merge them, version control them, build libraries. Like with a piece of C code, there's no special tooling needed. You can use this also with AI generation and so on. So it's just a piece of code. And we interpret this as also graphical diagrams. You can actually really modify them, and it's also the attached textual models are modified. So now, again, the test cases here, you can change them here. And for example, on the right side, you see if I change the test case, the sequence diagram is changed automatically. So that's the specification, the graphical specification for the textual model. And of course, I can on every level generate automatically those specifications. And they're really good to discuss in your team, especially when your test cases get a little bit more complex. For example, a test suite with hierarchies and so on. That's already pretty hard to understand if you want to discuss this with, especially with people that are not familiar with software development. So now we can generate the simulation and the test cases, and I can execute them with in this case, with a little graphical user interface. Here I connect with my system, with my test system and my system under test. They can be flashed completely automatically. So everything can run on command line, for example, for continuous integration, for complete test automation on any commit. Now I'm running this manually, trigger this manually. Now I'm while the test case is running, I'm pulling a plug to simulate some erroneous behavior here. And yeah, so we produced some errors. I'm fixing the problem again. Now you see the tests are okay. Those are, for example, those state transition tests I mentioned before, with a very high coverage for your system. And here on the right side, we see that something failed. So the activate BLC UART control or the speed range full sweep, those are test cases that actually failed. Let's have a look at the first test case. So here I ran into a timeout. So let's have a look at, such a second. Here, I'm clicking on the timeout, and in the development environment, I get exactly the place where the test case failed. So activate motor control, that's the activate motor control step here. Here you see only the single step. You can fix this if the problem is there. But in many cases, if it's a bit more complex, the problem might be somewhere here above. So for example, the same test step might work in a different test case, or in one test case it might work, in another test case it won't, because you have another context before. So, and in that case, this flat world logging is much more valuable than this hierarchical logging here, or this hierarchical system, because you need the context. But to develop, it's much easier to reuse those steps. So we have both views here. So it's a model, so we can generate views however we want. Okay, so that's been the demo. Let's wrap this up. So what are the best practices? First of all, do not test on all levels if you do not really need it. It gets really expensive. You can test on 10 levels if you want. Maybe that's not the best way to do it. So pick your levels that bring you the most benefit, or that you need for your safety requirements. But even for safety requirements, you do not need to test everything on every level. So be careful there. You can produce a lot of effort without really real benefit there. Then the system context of your system under test defines what you can test and the cost-benefit relation. So sometimes it's better to bring another chip into your system context for the test case or your test context, because it just gets easier to test. Sometimes you need to do it the hard way, because you might have a safety critical requirement there. So defining the system context is essential for the cost-benefit relation. Then do not strive for 100% coverage for everything. Focus on the risks. Even in a safety critical system, not everything needs the coverage of 100%. Focus on the safety parts with the MCDC coverage, for example, and better to separate them, the functionalities, into cores, into parts of the system, make a containment, and focus on the safety critical with system parts with a much higher coverage. But it could also be a priority based on not only safety, but also security or business risk. Could also be a prioritization. So prioritize your tests with risk-based testing. And start with an early and simple hardware-software integration test, especially for an embedded system. That's a very good way to start and to cover application level scenarios with a decent code coverage on the lower levels as well. And not 100%, but you get a really good code coverage on all the levels, and you find a lot of errors. And then, for example, fill the most important white spaces with the unit tests on a lower level, risk-based again. On the higher levels, you might need a system test or a big hardware in a loop system test. So it's a very good place to start. It's a sweet spot there. And use unit and hardware integration tests for test automation on every commit. That's a game changer, because you really know within minutes whether your change works. And you might have hundreds of software changes on a day. on a given day if you have a big project. The hardware changes usually every couple of weeks, later in the process every couple of months. So really try to automate what's possible, with cost-benefit relation in mind. Now, that's it so far from my side. Thanks to Hitex for the opportunity to be here again.